Are we ready? Okay, welcome everyone to Mechanical Engineering Seminar. This is our first speaker of the term who's been invited from another university. Our speaker was invited by Professor Dubieff, so I will pass off the introductions to Professor Dubieff to take over.
Thank you, Nick. And yes, we are extremely pleased to have Dr. Tony Sad today. Dr. Tony Sad is an assistant professor in the Department of Chemical Engineering at the University of Utah. He received his PhD from mechanical engineering at the University of Tennessee in 2010. And he works on fluid mechanics, but more specifically numerical simulation of turbulent flows and complex flows, especially involving reactions, chemical reactions. And he is a contributor, if I'm not mistaken, to the platform or library from University of Utah, UINTA, which is this awesome software that can do all kind of complex reactive flows in particular. And he's really interested in numerical methods, application of CFD, but also teaching computational methods. He has developed some awesome Python tools that I've been looking at. And I think, he also likes to enjoy, from what I understand, Utah and everything that it has to author, especially the beautiful spaces, as he has a passion for photography. And he really likes music. And I think this is why he jumped into the COVID-19 research bus. And I cannot wait to hear his talk on the simulation of the Opera House. So Tony, if you like to, it's a symphony actually.
Yeah. Thank you.
So Tony, would you like to explain exactly, or do you want me to explain? Yes. How about you explain?
I can explain it. All right. Well, first of all, thank you so much, Professor Fiorentino and Professor Dubieff, for the very nice introduction. And Professor Dubieff, I'd like you to write my eulogy, if that is possible. I really like how you introduced me.
Quite frankly, I don't. Yeah, I'm really hoping, I'm going before you, but okay.
Hello, everyone. Thank you so much for inviting me. It's such a pleasure to talk to you. Vermont is one of the places I haven't visited yet since I came to America, and it is one of the places I'd like to visit. Today's seminar is going to be a little bit different than what you've probably accustomed to or what you've seen, because I'm going to try to deliver a more engaging experience, I hope. And the way to do this, you see the green screen behind me. I'm going to try to use that green screen to put myself in my slides so I can move around and put my finger at the videos, etc. But to do this effectively, I need to do it through a live stream on YouTube. Now, most of you are tech savvy about YouTube and Facebook live streams, etc. I wasn't. I learned a lot about that recently. So I'm going to share with you a link now to the YouTube live stream where I will deliver the seminar. Now, once we go on the live stream, once I share my link, I am going to mute myself and close my video camera on Microsoft Teams. I would also like you to mute your microphones because I can still hear you through these earpieces. And the audio of the conversation is also channeled through YouTube. So I'd like you to mute yourselves. And then once the seminar, the live stream is over, I will switch back to Microsoft Teams and we can have a discussion about all the work. So are we in agreement? Yes, looks like we are.
I think everyone's muted.
Okay, great. That's even better. Now, I'm going to put the Microsoft Teams screen next to me. And once the live stream starts, I just want you to give me a thumbs up that you can hear me. Okay, there's a 10-second delay between me and the live stream. And so once you start hearing me on the live stream, just give me a thumbs up to make sure that everything is going well, and it will not distract me. Okay? Thank you so much. All right, I will see you on the other side of the internet. Okay? Hello, everyone. Thank you so much again for this awesome invitation. I'm very excited to be here with you today to talk to you about some of the exciting and fun work that we did over the summer for the COVID-19 pandemic for the Utah Symphony. I see some of you are smiling, which tells me that you can hear me well on the YouTube stream, and that's really great. I hope this talk will be as fun and engaging as the work has been for all of us. So again, I want to thank Professor Dupief, Professor Fiorentino, the Mechanical Engineering Department at the University of Vermont for inviting me. We can get into the talk today. Clearly, as the title designates, I'm going to be talking about something related to COVID. And my background is in mechanical engineering. And when this pandemic hit us all, I always thought, like, what can I do as a mechanical engineer and a chemical engineer as well? As an engineer, what can I do to do something to help with the pandemic? And specifically for those of us who are working in computational fluid dynamics simulations and scientific computing, not specifically in the public health sector, what are we going to do for that? And this project came to us as a blessing and as an opportunity to teach us that us engineers, we can do a lot of fun things to help, a lot of good things to help the community. First, I would like to thank my team and thank the funding to get this out of the way. This is my team on the left. My co-PI, Professor Sutherland, standing next to me. I'm the shortest of all. I got my student Mokbel over there and Hayden over here, and a postdoc working with both of us, Dr. Josh McConnell. I thank the entire team for the great work they did, for the hours they spent doing this, and I'm here to take really credit for all the great work they've done. And I want to thank the Salt Lake County who funded this work, and the Utah Symphony and the Center for High Performance Computing, and definitely our chemical engineering department. All right, so on June 23rd, I wake up very early because I have two kids, but I get an email at 10 o'clock in the morning from a Dave Pershing. Professor Dave Pershing is a faculty in our department, and he was the former president of the University of Utah. Now, when Professor Pershing sends you an email, you drop everything you're doing and you go and read that email very, very well. And apparently, a person called Pat Richards reached out to him and asking for help in the work they do. And Pat Richards was the interim CEO of the Utah Symphony, Utah Opera. So we're going to call this USUO from here onwards. And they needed help in understanding the impact of COVID-19 for performance. So Professor Pershing, thinking that this is an aerosol type problem that could use some computing, he emailed us. We had never thought of that before, but once the idea arrived to us, we're like, this is interesting. Maybe we could do this. Now you ask yourself, why would the Utah Symphony need to figure out what's going on their stage with COVID-19? Well, if you think about it, an orchestra consists of string instruments and percussions and pianists and people standing, etc. All of those can be masked, maybe even double masked or triple masked. However, there's a huge section of any classical orchestra that includes people blowing into their instruments. Those are the wind instruments, brass and woodwind, such as the flute, the oboe, the trombone, the trumpet, all the brass instruments and all the woodwind instruments. And if you've played any woodwind instrument, those instruments collect a lot of respiratory droplets that tend to break up. And once they break up, they come up into the air as aerosols and they move around. So if one of them is infected, they might end up infecting the entire woodwind assembly and potentially even others, even with the masking. And so once we realized that, we're like, yeah, this is a legitimate problem. Now, how can we help? So we had, just to put things in context, they wanted results by September, and they reached out to us in June. By the end of June, it takes a week to get the project processed through all, the university channels. So we barely had 10 weeks to get this done. Okay. Now you might think, 10 weeks is a reasonable amount of time if we're working nonstop on this, and we're like 5 people working on it. However, to put things in context, clearly we ended up doing simulations, but each calculation consisted of about 1,500 million grid points. That's not too much, but that's not too little either. These are large eddy simulation calculations. Took about 5 days to finish each calculation, although we were using high performance computing, about 1,000, 1,100 cores, or 1,100 to 1,000 cores through a generous donation of CHPC. And data analysis was a nightmare. If you've done any serious CFD, you are talking about huge data sets, talking tens of terabytes of data accumulated. Remember, we're tracking all the instruments and all the airflow, all in 3D. Different instruments had different aerosols being transmitted. So it was a nightmare dealing with the data. Just as an example, it would take 1 day to just generate a simple time average over the entire duration of the simulation. So we said to ourselves, yeah, we want to do this, but are we out of our minds for doing that? James and I were talking over the phone, and we said, yeah, let's do it. You know what? And I am so glad that we were out of our minds when we did that decision. Okay. So how do we approach the COVID-19 transmission modeling as computational people or as engineers who understand fluid mechanics, who understand transport of particles? Based on the little we know about how viruses transmit, we think that viruses attach themselves to respiratory droplets. These are the droplets that show up when you're talking, when you're sneezing, when you're coughing. Now, some of those droplets are large enough, they fly out and then they just deposit. This is the 6-foot social distancing rule that's very, very outdated. That applies only to the large particles. You can do a calculation show that 6 feet is like a reasonable settling distance for these large droplets. Now, those droplets, if they're contaminated, they lead to surface contamination. Are we worried about that? We're not, because they're sweeping the floors all the time. They're cleaning up the surfaces. They're spraying hand sanitizer, everything. We're not worried about surface contamination. What we're worried about are the remaining droplets. They end up breaking up and into very, very small droplets that are called aerosols. And by definition, aerosols are airborne. They just suspend in the air, and they can go anywhere that the airflow goes to. There's no 6-foot distancing. It could, if you are standing downwind of a fan and you sneeze, and those little droplets are going to fly 20, 30 feet away. They might evaporate for sure, right? But they're still flying around in the air, and they may infect a person at a longer distance. Okay. Now we said, okay, we're not worried about the large droplets because surface contamination is not a big deal for us. We are worried about the aerosols. So if we assume that all the wind instruments are emitting, let's just focus on the aerosols, then we have a way to solve this problem. If wind instruments emissions are only composed as aerosols and aerosols follow the airflow, then we can simply model all of those aerosols as just a tracer, as a scalar tracer, essentially just an advection equation, diffusion coming in from numerical errors, but essentially just an advection problem. Now, we could have modeled the aerosols with Lagrangian particle transport, fancy term for those who are immersed in CFD, but first, that would have been an overkill, and we didn't have the time to do it. We had barely 10 weeks to do this project. Okay, so we decided, okay, aerosols, they have these very low Stokes numbers. We can just model them as tracers. And then when you think of that, if we capture the airflow, we add the tracers from the instruments, we can track the virus. And that leads us to CFD, computational fluid dynamics. So that analysis allowed us to bring that problem of the potential for infection in the symphony into things that we can understand and deal with as CFD. What I'm showing here is a little simulation showing you a little piece of, think of it as an incense with a little fan blowing over it and showing how that emission moves around with the air. Okay, so this is exactly what we ended up doing. All right, so I want to get some of the limitations out of the way so that we can enjoy the rest of the talk, understanding the limitations of our study. We are not providing recommendations on whether to resume activities or not. That is not in our purview. It is something that we might attempt to do in collaboration with someone from health sciences, like doing a dose response model, a probability of infection analysis, etc. But we're not providing that to the orchestra. All we are telling them is, look, if we assume that all aerosolized droplets are infected, and we can track where those droplets and where those aerosols end up, then the higher the concentration of the aerosols probably means you are more likely to get infected. And the lower the accumulation or concentration of aerosols, then you are less likely to get infected. So what we're going to provide the orchestra with is sort of a three-dimensional map of where we have accumulations and where we do not, and what to do to mitigate those accumulations. Okay. Droplet or aerosol distributions were not considered. Again, we could have considered that with Lagrangian transport, but that was not the primary problem. We are interested in the bulk motion of these aerosols in the hallway. Now, this is a stage. This is a huge stage. The computational effort needed to do this, if we were to resolve even more dynamics of these aerosols, would have been tremendous. I think it would have been an overkill. So we did not consider droplet size distributions. We assumed all emissions are coming from, have just one distribution traced as a scalar. And we did get the information, however, from a study at the University of Minnesota, where they looked at droplet size distribution and concentrations from different instruments. We took the peak concentrations, the worst case scenario. Why did we do that? Because it kind of tends to compensate for any of the issues we were doing, for any of the errors we were committing elsewhere. So it tends to balance things out, and we were looking at the worst case scenario. Now, as we go through this talk, we are going to distinguish between two types of instruments. There are super spreaders and super emitters. Super emitters are instruments that emit a lot of droplets, but not necessarily at high speed. So the trombone, for example, emits a lot of droplets, but at low speed. Now, there are the super spreaders, on the other hand, that emit droplets at a very high speed, jets, so they shoot it out. The flute is one of them, but a super spreader is not necessarily a super emitter. Now, the worst case scenario, if you are both a super spreader and a super emitter, like the trumpet, which was the worst of all instruments, the trumpet emits a large number of droplets, a high concentration, and at a very high velocity. They have the potential to essentially overwhelm the entire stage, as we will see. All right. And again, the last thing we did not consider is the interaction between the stage and the house. The house is where the people sit, the audience sits, and the stage is where the orchestra plays. Now, a well-designed ventilation system, better than the one in the building I'm sitting in, and that's like a 30-year-old building that we looked at, the ventilation is separated. The stage ventilation is different from the house ventilation, and right at the screen there is sort of just a dead zone. There's no air exchange, in other words, between the stage and the house, and we ended up verifying that for ourselves. There's very little air exchange, so we're not worried about the exchange of the air between the stage and the house. And the house air conditioning is really nicely designed. There's there are inlet vents above almost every other seat, and there's the return vent under every other seat. So there is flow coming from above all the way to the people sitting there and under them. Okay. Now for the CFD Minded, we used filtered large eddy simulation equations with dynamic Smagorinsky model. We used first and second order Runge-Kutta strong stability preserving schemes, all explicit because our code is structured. We favor explicit methods over implicit methods. The timescales were relatively the same over here, so an explicit method would do just well. We used flux limiters on all convective schemes, even on momentum. Although we had turbulence turned on just to help stabilize the flow, our resolution was around 5 centimeters, and our time steps were between 10 to the minus 4 to 10 to the minus 2 second. We did not consider any thermal physics. We could do it, but again, we did not have any reason to believe that is going to be make a significant effect in our case. And the chamber is maintained at a very fixed temperature and humidity level. Instrument emissions were modeled by adding a source term to the scalar transport equation where the instrument is located, and that source term emits a certain concentration at a certain velocity. And many instruments were under-resolved. And by under-resolved, I mean that we had a 5 centimeter grid resolution, so that's the size of our grid. Now, the flute is, let's say, 3 centimeters opening. Clearly, we cannot represent it within that grid cell. So we ended up, the flute, for example, would end up being a 5 centimeter opening, but we adjusted the flow rate so that we can match the concentration being emitted by the flute. So we had a trouble with a couple of those instruments. Otherwise, we wouldn't be able to do the calculations. All right. So now on to the first test case. Now that we got some of the science settings out of the way, the first scenario we considered is what's called Abravanel Hall. That was named after Maurice de Abravanel. He was a Swiss guy who came to Salt Lake City in the 20s, and he ended up being the first conductor of the Utah Symphony. Abravanel Hall used to be called Symphony Hall. It was the first symphony house in Utah, built in 1971, around 1971, 1972, I believe. And he was the first conductor, and it was the hall was first named Symphony Hall. It was later named after him. And this is exactly what it looks like. It's a really beautiful place. If you ever come visit us in Salt Lake City, we'd be happy to accompany you to listen to the Utah Symphony and Opera. All right, so now this is an actual picture that I took of the stage, and my green screen behind me allows me to be in that stage as if I'm right there right now, maybe to a certain extent. Now I want to orient you a little bit about what's going on. There are inlet vents at the ceiling up above, as you can see here, if I can put my finger just on it. All of those horizontal lines, they are inlet vents. Now, it's not completely inlet. There's an inlet, and then there's a gap, then there's an inlet, and then there's a gap, there's an inlet, and there's a gap. I'll show you a picture from behind it. So those were the inlet vents. We clearly needed to capture those vents. Now, what's also important is that there is a door over here and a door over there. Those turned out to be very critical in our mitigation strategy. So I want you to remember those. And there are a bunch of return vents. We stand over here, bunch of return vents over here as well, all the way across the back. Okay, all the way across the back, there are a couple on the sides as well. Okay, and that's the team trying to take measurements. If you can tell, there's my co-PI, James, over here. I'm behind the camera. And up there on that lift, now if you can focus, Hayden, he is the daredevil of the team. I tried to go on that lift. I was like, nope, it was shaking a lot. So I was scared. I went down, told Hayden, you go, you go and do it. He likes all that sort of adventure. That's us still taking measurements over here, Hayden taking measurements. Now, I should tell you that we had the 10-week timeline. Actually, that timeline shrunk down to about 7 weeks. Because early on, we wanted to get the boundary conditions, essentially the inlet velocity and the return velocity of the chamber so that we can put those numbers in our simulation. And Salt Lake County hired an HVAC company. Supposedly, they're the experts in getting measurements. So they went down, they did all sorts of things. They did measurements, and they came back and they gave us a spreadsheet that the velocity is 0 everywhere. And like, this just doesn't make sense at all. We wanted also some data points across the hall just to do to get some sense of verification later after we finish the simulations. Their velocities were just zeros everywhere. There was like one cell that had 0.1. And we emailed them, was like, that doesn't make sense at all. And one of the people responded to us like, it has to do with turbulence. And so we rolled up our eyes, rolled up our sleeves, and got down ourselves and did the measurements ourselves. Velocities were not 0. We took several measurements and took an average just to get a sense of where we're at. We compared that with the design numbers that were provided to us by the Salt Lake County, and we were very close to those design numbers. So we felt confident. There is still some uncertainty there, but that is not going to affect the bulk motion of the flow, as you will see later. Okay, this is a picture from above the hall. As I told you, this is an inlet vent, okay, and they get fed from these ducts in the back. There's an inlet vent, and there's a gap over here, and then there's an inlet vent. You can see it in this picture. This is the inlet vent, and these are the supply ducts. Okay, great. All right, now, next, we have an idea of what the chamber looks like. And even while we were waiting for that company to give us the numbers, we went to work. We did the geometry for the chamber. We put in some of the design spec numbers that were given to us on paper until we got the actual numbers for the inlet velocities and the return velocities, etc. But in the meantime, the Utah Symphony gave us their original arrangement, or the arrangement for the orchestra. Now, this is going to be critical for us. That's why I wanted to introduce the arrangement. So this is what their orchestra looks like. It is a socially distant arrangement. And if you think about it, orchestral arrangements have been in the making for centuries. And I don't know how they quite do them. I think each hallway is going to be different because it depends on the acoustics of the hallway. But there are general guidelines, I imagine, for how orchestras are designed. They typically try to cluster certain types of instruments together, and so that they don't, over sound other instruments, etc. This was the arrangement given to us. Okay, you can see the violins and the strings are all up front. And in the back, there's percussions, but in between, all of the instruments that are colored, all of the dots that are colored, not blue or gray, they are wind instruments. So there's a lot of wind instruments in this particular arrangement. Okay. Now, the data that we got from the University of Minnesota study had to do with concentration and volumetric flow rate. And from the volumetric flow rate, we were able to extract the velocities. But these are just a bunch of numbers. I'll display them in a nicer way in the next couple of slides. But those were the numbers that were given to us. And just to kind of fix ideas a little bit in your mind, the trumpet is a super emitter, because it emits a lot of droplets. From the flow rate, we don't know yet if it's a super spreader, but once we calculate the velocities, we're going to recognize that it is a super spreader. Now, this is my interpretation of the arrangement. I'm going to step out of the frame a little bit. There are two things that you're looking at. There is size and color. Okay, the size corresponds to the concentration. Okay, the larger the size, the higher the concentration of aerosols that the instrument is emitting. For example, the trumpet is the largest. It is the most emitter. It is the super emitter over here. And then you go down to the flute, it is the least of all of those, right? Because the size is small. And the size is given by this table just behind me. Now, the second dimension you're looking at is the color. And my color map goes from blue to red. Blue means low, red means high, and it indicates the speed of the jet being emitted. The redder the color, the more of a super spreader the instrument is. Again, the trumpet stands out. It is a super emitter and a super spreader. The flute is not a super emitter, but it's a super spreader. The trombone, like I mentioned, it is a super emitter, but it's not a super spreader. And so those are going to we realized those things after we did the simulations. We're like, yeah, this kind of makes sense. Let's kind of think about it in a different way. Okay. So before we start looking at the strategies. Let's just analyze the base flow field. And if you've done CFD in your life, or if you're just your engineer who wants to understand fluid mechanics in a region, you want to understand the flow field first. Have a look at the flow field. What I'm showing next is our simulation of the stage. You see the individual instrumentalists we put cylinders. We don't think the flow is going to interact with the structure of the human body. Just put in cylinders there. We could put more complex geometry. It wasn't worth it. And then next to each instrument, we're going to have an emission source, as we will see later. But right now, I'm going to look only at the flow field. So what I'm going to show next are the contours of the instantaneous velocity. That's the speed, the velocity, magnitude of the flow shown on a log scale. Okay, the color map goes from 0.1 to 0.5 meter per second. These are very kind of quiet and nice flows, very comfortable. You can see from the top over here, you can see the distribution of the vents. And I'm looking into the stage, and that's how the stage looks like, okay, with the instrumentalist. And I've taken 3 slices across the stage to show how the flow looks like. You will notice that right in the back, there's some red. That's where, that means high velocity. That's where the return vents are. So let me play this. I'll let you look at it, spend some time looking at it. What you will notice is the formation of a few dominant structures. There is a lot of local mixing and local dynamics going on, but critically and more importantly, you can distinguish just two large structures when looking at this. And this one gives it up. There is a large recirculation, this large vortex, we call it the frontal vortex, that shows up over here. And there is one in the back. Okay, now the one in the back is not only rotating this way, we will see later that it's also rotating across the plane. And then in the middle, you see something similar, not as pronounced. So it turns out that this vortex over here and this vortex, they are kind of localized over there. In the center, there's more sort of a uniform mixing, okay? And then this is a front view of taking a plane across the chamber. It's very comfortable, really, on that stage. These velocities are not very large, but they cool the area really well for a very comfortable environment. Next, I'm going to show some streamlines, and just to confirm that there is this recirculation zone over here, and then there's this other recirculation zone over here, and in the middle, it kind of is just all well mixed. There's not a definite structure. Now, when you look at the top, you can see the vortices in the back, but they're also counter rotating, but into the plane. And from the other side, you could see it kind of rotating upward, I think. Okay, that's good. Now, okay, we looked at the flow. What is critical now is let's look at these aerosols. And like I said, we just did tracers for each instrument. So this is the initial condition here, or one time step into the initial condition, showing all the wind instruments and their emissions. You will notice here, and we'll discuss this later, this is the flute. There are 2 points in the flute. That's the flute outlet and the flautist, where the reed is, and there's some flow coming out. So it's got 2 exit points, the flute over here. All right, so I'm gonna play this and let you just, let it sink in. We are tracing particle concentration. So what you're going to be looking at are contours of particle per liter. And I'm going to show 3 colors: 0.1 particle per liter, 1 particle per liter, and 10 particles per liter, going from yellow, orange to red. Okay, I'm going to play this. So we are assuming all the instruments are continuously playing. And you can see that these aerosols, they just follow the flow field as expected. You see the red big spots back there where the trumpets are, and further a little bit up front where the bassoons are. And then it goes light, and as the flow moves, as the aerosols move in the domain, they dilute, they turn more yellow, they reach up the top, etc. But just visually, qualitatively looking at this, assuming the worst case scenario, that these instruments are continuously emitting. Now, clearly in real life, that's not the case. They're going to play a little bit, they're going to shut up, and then they're going to play a little bit. But that'd be just too much to do in a simulation. We thought if they're continuously playing, okay, for 20 minutes, whatever it is, and they're continuously emitting potentially infected particles, this is a bad thing to look at, all of this accumulation. And now this is all qualitative. Now we wanted something a little bit more quantitative to give us a better representation of what's going on. So what we did, we thought, okay, what I care about is if there are any infected particles or any droplets that are within my breathing zone, my mouth and my nose, okay, specifically my nose, my eyes, my ears. So what we did, we took a region from about the chest level to just slightly above head level. Now, these instruments are seated, so we took that from 90 centimeters to 130 centimeters, so that will be just above here if you're an average person. And then we took the spatial average vertically and a time average across the entire simulation, okay, to give us just a more simple representation of what's going on. If I'm sitting in this breathing, we call this the breathing zone. I don't care if there's a particle hanging up above me over time. I don't care about that. What I care about is what's in my breathing zone. So it gives us better kind of control of what to expect. And this is what we got, okay? What you're looking at are contours of particle concentration, but those are both spatially and time average. So on average, this is what you will be exposed to. Blue, dark blue corresponds to 0.1 particle per liter. So that would be this area over here near the stage and this area over there. White is somewhere between 1 to 5 particles per liter. 10 particles per liter starts turning orange, and red is 100 particles per liter. And to orient you a little bit more, this is what you're looking at. The trumpet is both a super emitter and super spreader. So you can see very large red, you can see red values next to it. That's high concentration, and it's spreading everywhere. Now, because of the airflow, it's moving all of these aerosols to the back, right? Poor percussions and trombone, okay? But it is a super emitter. Now, you look at the flute is not a super emitter. Remember, it's got a small disc size, small circle, but it is a super spreader, and you see it flooding the poor strings in the front. Same thing for oboe. The bassoon is not so much of a super emitter or a super spreader. The clarinet is a super spreader, but not so much of a super emitter. The French horn is one of the nicest. Anything French is very nice. All right, so we're looking at that picture. That's a problem, because looking at that, we are going to be exposed to some dose of potentially infected particle. And for a normal breathing rate, that's about 14 liters per minute. I saw Yves just do a thumbs up to me, thumbs up to the French. And so looking at this was not a good setting. That's the baseline setting. So what do we do now? Okay, we said, okay, should we put enclosures on the instruments? How is that going to play out? There's a lot of scenario variations. There are limited budgets. Remember, these orchestras were out of commission for a long time. They were really struggling. And if you look at the statistics of the amount of losses that the performing arts have suffered, especially orchestras, it's huge. And so we wanted a strategy that is simple and cheap, really. That's what engineers do, okay? So we came up, and that's in retrospect, with the car smoker analogy. Okay, so I want you to think with me for a minute about this. Suppose that for some reason, you must transport an individual who is smoking a cigarette in your car. I grew up in Lebanon, and everyone smokes over there. And you're always having someone smoking in your car. Okay. Now, you might like that cigarette smell, or you might not. Most people do not, and so it kind of looks like this, all foggy. So what would you do if you were obliged to transport someone in your car that insists on smoking a cigarette? Okay, what would you do to minimize your exposure to the smoke? One, you'd probably roll down all your windows, blast the AC. Why? Because you want fresh air to replace all that smoke that is being constantly emitted. And you want a pathway for that fresh air to just come in through the windows and leave. Okay, you probably mix everything up, but you're gonna dilute it. You're gonna dilute the heck out of it. Okay, so you open the windows, blast the AC, keep the car moving just to keep fresh air coming in. Next, you would probably ask the smoker to sit way in the back and probably as close to a window as possible. All right. So this is exactly what we thought we could do with the Utah Symphony, or with any orchestra for that matter, or any situation in retrospect. Opening up the windows is equivalent to us manipulating the ventilation at a Bravenel Hall. Now remember those doors I mentioned to you? We are going to open those doors and see what happens. Of course, we can play a little bit with the ventilation. I'll tell you a little bit about that. That did not have a major effect. We ended up settling on 80% return, so that 20% of the air leaves through the doors. We tried to change that to 60% return, so that 40% of the air leaves. It didn't make a big difference. So we just settled on the 80% throttling of the HVAC. But asking the smoker to sit close to the window is the equivalent of going to the conductor, Thierry Fisher in this case, and telling him, we need to rearrange your orchestra. We're going to place the super emitters, the super spreaders closer to the return vents, closer to the doors, put the lower emitters and lower spreaders somewhere in the middle, and move things around. And if you think about it, that's a very daunting proposition, right? We are taking an orchestral arrangement that's been in the making for hundreds of years, and we're using our engineering judgment to change that. We'll get to talk about that after in our discussion, but the response to that, thankfully, the orchestra was open to anything to keep their players safe. And in this entire project, we were meeting with the entire symphony, with all the players, just regularly, about once every 2 weeks, to tell them what we're doing. And they were also supportive of the work because it appears to have given them a sense of certainty in this time of uncertainty. All right. Now, again, in retrospect, and as we got some public attention about this, we came up with the slogan, says, if you change the airflow, you change where the aerosols go. The way we said it, we said we change where the droplets go. Not everyone understands what aerosols are, but this was to stress the fact that if you manipulate the air conditioning, if you manipulate the HVAC, if you change the air surrounding you, you are going to change where those potentially infected droplets go. So we went with that slogan, and then we ended up doing several scenarios. We looked at 5 seating arrangements, and we did this by hand. Now, luckily, Hayden is a classical music connoisseur, and he knows all about classical music. So he was a godsend to us in terms of thinking about rearranging instruments. He knew the ins and outs of where instruments should be located, etc. So that was very helpful. We looked at 5 scenario arrangements. I'm not going to bore you with all of those. I'm just going to show you the best arrangement that we found. All was done by trial and error. And we looked at 3 HVAC variations, closed doors, open doors, 80%, 60% ventilation. I'll show you only one, the most effective of them. In total, I think we did actually more than 20 full simulations for about 500,000 CPU hours. What's a CPU hour? It's just essentially taking a single CPU, and if that CPU is spending 1 hour uninterrupted on your calculation, that's by definition a CPU hour. So we had 500 CPU hours spent on this. So if you had one single computer running all of those calculations, it would have taken it 57 years. So that's the equivalent 57 CPU years. And this is the power of high performance computing. If it were not for parallel computing, there would be no way on earth we could have finished this project. All right, I'm going to talk about the 2 relevant cases now. The first idea was we opened the doors. We kept the original arrangement because that was the least intrusive change to the orchestra. All they had to do is open the doors. Those were huge doors. Okay, so this is what happened. I'm going to show you the concentrations. Okay, again, same orchestra playing. I'll step out of the way over here. Now, for reference, you can see the original case down there. Now, what you notice is that the instruments close to the door, they just have a quick exit. Now, we didn't finish this simulation because we knew it was not going to make a major difference, but it was going to be critical for the next step. So what we found is that opening the doors was not sufficient. because most of the emitters, most of the smokers were still seated in the middle, and there was not much air being dragged from the center all the way to the door. So in other words, the extent of the effect of the doors was not felt to the center, through the center of the domain. And this is confirmed by these streamlines. I'll show you the ones from the top. You see two color streamlines. The purple streamlines are streamlines that are exclusive to the open doors. So in other words, they show you the extent of the effect of the doors, and that extent was not really pronounced. It only covered the pianist over here and maybe one instrument, and then it covered, I think there was a clarinet over here, okay? And only that. The remaining streamlines were kind of the whatever was in the flow. And you can distinguish now, for the next step, I want to distinguish these two regions, and I also want to distinguish these two regions up top where we have returns. So anything in purple now, in these purple boxes, is showing you where return vents are, or where those open windows are. The smokers are still in the middle, and now we come up to our next challenge, which is the modified seating arrangement. Okay, so I'm going to take the original seating arrangement now. I'm going to try to stand out of the way over here. Actually, over here, I'm too close to the lighting, so starting to disappear. All right, so I'm going to stand out of the way and explain to you what we did. I'm going to first overlay this picture of where the extent of the return vents are. Okay, this one and this one over there. And I'm going to move all percussions out of the way. These instruments are, we can move them around. The strings, they have to be out front. Okay, otherwise, they will not be heard. Okay, so we kept the strings out front. Now we look, all right? So first thing I want to do is try to move the trumpets as close to return vents as possible. Those trumpets are both super emitters and super spreaders, right? So they have a large circle size, okay? And they are red. So they're both super emitters and super spreaders, and move the trombone around. Now, trumpets and trombone, they go together, so that's why we put them next to each other. However, the other pair of the trumpet is over there. You know, that could still work from an orchestra perspective. Then we took the clarinets. Those were our next super emitters. They're not quite the super spreaders. They're somewhere in between, but they have this large sizes to emit a lot of aerosols, and then we put them in the back. Then we moved the flutes over here. We moved the French horns over there. Put the oboes kind of in the back. They are slightly, they emit quite a bit. They emit okay, somewhere in the middle, but they are not super spreaders. So they have low jet velocities. And we put the bassoons over here. And then we put back the orchestra. And we have a new orchestral arrangement using computational fluid dynamics. Maybe that should be the title of the paper. Using CFD to redesign an orchestral arrangement, right? Now let's see what happens. Okay, I'm going to step out of the way and let the video play. This is with the modified seating arrangement. And just qualitatively, looking at these 3D calculations, you could tell that this had a very large impact on the accumulation of these droplets. All the instruments are within the region of the return vents or the whatever outlet there is, okay? And that helped us tremendously. I'm gonna let this video play for another second. And when we saw this, it was such a relieving thing to see that we could do this. All right, so next I'm gonna show the breathing zone time and spatial average. This is the original arrangement, the simulation, and this is the open doors and the U-seating arrangement. And if you do the calculation right, you can show that we reduced on average the accumulation of droplets by a factor of 100. And that was significant, okay, that was significant. Could we do better? Sure, but we really ran out of time. And this was a very small funded project. It barely covered any of our time. But it was one of those projects that the rewards of are so much more than any monetary compensation and or coverage of your time. And I'm on tenure track, and I need to be looking for projects that support me in the long term. But to me, this project was a strategic move because it helped me enter that spotlight of being plugged into the community with the work I do. So if there's a message I want to give to the students here is that, yeah, sometimes these projects are so much worth it because their rewards are intangible. You don't know what's going to show up. Like my communication with Professor Dubief was a result of this particular project, and I ended up being invited here. And who knows what will happen next, right? Okay, a more quantitative analysis. Essentially, we looked at the breathing zone and we calculated the percentage of the breathing zone that's occupied by a particular concentration and plotting on a semi-log scale. So on the x-axis, you see the log of the concentration. So -3 is 10 to the -3 particle per liter, -2, etc. 0 is 1 particle per liter. 1 is 10 particles per liter. The blue line is the new modified open door arrangement, and the red line is the baseline. Now, what you see with the blue line, we moved all the accumulations towards the smaller particle concentrations, about 0.1 or less. So in other words, most of the breathing zone is occupied by particle concentrations of less than 10 to the less than 0.1 particle per liter. However, the original arrangement was occupied by concentrations 0.1 to 1 to 10 particles per liter. And this is significant. Okay, now, how do we put this to the test? There's this Lebanese-American author called Nassim Nicholas Taleb. He wrote this book called Skin in the Game, and that's essentially the equivalent of talk the talk and walk the walk. In other words, if you have something to say, if you have advice to give to someone, are you putting yourself at risk of that advice? So if you're taking investment advice from someone, the first thing you ask is, are you investing in those stocks or whatever? I go to the doctor and the doctor recommends a procedure for my kid. I was like, would you do this for your kid? Show me that you've done this for your kid. So, it's one thing that we like to test, and I personally like, and this is our skin in the game. In other words, with those results, I was willing to go stand on that stage or sit in the audience, even unmasked. Now, they had us wear masks, but I was willing to do it even unmasked because I trust our results. And this is evidence of that. The Utah Symphony invited us to their first return performance. And I'm going to play the video. I hope you can hear the audio. I was struggling with the audio a little bit early on, so I'm going to play the audio. Now notice the following. See the open doors? And I saw the open doors. I got goosebumps. And to me, there is no better evidence that I stand by my results than us going and sitting in the stage. And we ended up standing on the stage and talking to the instrumentalists, etc. All right. So with that, I think I'm going to conclude the talk. We ended up doing the same thing for another theater in Salt Lake City called Capitol Theater. I'm not going to go through the slides. I'll just scan through them. But we had a similar story. It was a little bit more difficult, but to fix in this case. But we were looking for doors, and we've never been excited about doors as we have been after this project. And anyway, we did the same thing. We ended up figuring out a new arrangement and a new way for opening the doors, and we ended up designing a plenum for the Capitol Theater. And this is the final result: is that with the plenum and with the open doors, we were able to take all of those aerosols out of the way. All right, and same story we can tell about Capitol Theater. We think it was successful. Now, on to conclusions before I put out some perspectives. After this project, and in my opinion, any pathogen dispersion analysis is not complete without fluid dynamics. Anyone who tells you, oh, you should be okay standing 6 feet apart, that does not make sense. You need to look at the fluid dynamics of it. Without fluid dynamics, I will not trust any result, okay? CFD then becomes a valuable tool in the arsenal. Now, the problem here is bringing the engineers with the health sciences so that we can communicate with each other about the importance of the CFD before doing any viral transmission analysis. The scientists on the other side, on the other camp of health sciences, they're worried about, how the virus behaves and its life, etc. Well, if the virus doesn't arrive to you, you're not going to catch it. I don't care about that. What matters, the first order of business or the first order issue, is understanding the fluid mechanics, and CFD is the critical tool in that area. Our recommendations, although we couldn't do generic recommendations, these are specific to the boundary conditions and the conditions of individual, the hallways or the concert halls that we were looking at. We were able to get general recommendations to encourage air replacement by opening doors, opening windows. For my house, there's something called a house fan. And, in my case, we have a newborn baby and we have a nanny that comes and helps us. And we want to make sure that she feels safe. We want to make sure that we are safe, even with masking, and the air conditioning at home doesn't have that overpressurization power that you get from large buildings. So we're considering putting in a whole house fan. These are huge fans, like huge exhaust fans. You put them in the attic and then they replace the air in your house within a couple of minutes. So you open the doors, turn the fan on, you replace the entire air. You can run this every 15 minutes if you're really worried about this. Now, if there are allergens out there or some air pollution, you probably don't want to do that. But, on a nice day, you can run this every 15 minutes. It's very pleasant. Place the super spreaders closer to vents. So those are the high velocity jets like the trumpet and the flute. We clearly need more high resolution calculations to develop low order models for emissions. We just put in a scalar transport and move that around. There are clearly other effects that we might need to consider over there. A similar analysis can be applied to offices, cubicles, clinics, hospitals, airplanes, etc. There are some in the literature who are using RANS type simulations. I'll talk about that in a second, for airplanes or public schools. Now, in retrospect, to do the seating arrangement, or if you think about it, a clinic rearrangement or a bus rearrangement, etc., this is where AI can be helpful. In that if you feed it a very low-cost simulation tool to run scenario variations, it can probably find an arrangement for you that, for example, minimizes the exposure concentration within a certain amount of time. Okay, and we definitely need low-cost CFD models for faster around simulation. So imagine we could have done this with similar accuracy, but within a day's worth of time. That would have allowed us to do more scenario variations as well. Okay, and before I conclude the talk and we switch back to Teams and have a discussion, I want to throw in a little discussion about what I learned from this. This is a new application to me. My area is doing the fundamental under the hood numerical methods and algorithms for CFD. I don't care what they're applied to. I'm really interested in the time integrators, spatial discretization, these sorts of things. But this application, gave me a perspective on these types of problems and what's in the literature. So if you plot on the y-axis, if you plot model complexity, starting from the simplest models you could imagine. So just doing like a mass balance on a chamber and move a scalar around. So you're not even satisfying momentum. And all the way to the most complex type of simulation, direct numerical simulation with Lagrangian particle transport, and you're solving the whole thing. And in between, you find Reynolds averaging with scalars, maybe with Lagrangian, large eddy simulation, etc., large eddy simulation with scalars and with particles. And on the x-axis, you plot the simulation volume. Okay, so that's the size, the entire size of the simulation that was conducted. And what I found in the literature is what I call the cookie box. These are like very simple simulations to illustrate what you could do with a certain method, and all the way to a football stadium, for example. I didn't find a football stadium simulation, but a concert stage is where we're at, an emergency room, an airplane, a school bus, etc. Then what you find in the literature is the following. You see a cluster of studies doing the very complex models, but on the small volume simulation, on the small volume scenarios. And you see another cluster on intermediate volume calculation scenarios, but at a lower fidelity. So most of those are RANS calculations. There are a few doing LES with scalar, maybe Lagrangian, but further over here. So this puts our study with the concert stage and LES and scalar over here. Okay, so that gives us perspective where we're at. However, what I'd like to see is using the very high fidelity models to inform low cost and fast turnaround models. What we need is not an LES calculation that gives me the details of how the flow moves. What I want is, I'm sitting there, on average, what is my exposure level? So we need a tool or methods that are accurate just enough with a quantifiable uncertainty that can tell us, that can do these simulations really quickly, right? Some of the other outcomes, we had an NIH proposal submitted, was rejected last week. Unfortunately, it was a big team. We tried to bring in people from virology and health sciences. We heard back last week, so I put reject. I didn't delete the line. We had a few interviews here and there. The best one was with NPR Utah, so that was like once in a lifetime interview. So that, when I talked about the rewards, those are the rewards you get from this, and it's a very humbling experience. I'm organizing a mini symposium on CFD and COVID-19 for the upcoming IAA 2021 CFD conference, and I'm hosting guest editing a special issue on CFD and COVID-19 with the International Journal of Computational Fluid Dynamics, and Professor Dubief has volunteered to contribute a paper over there, and he's also reviewing for us in that journal. And with that, I conclude my talk. Now we're going to switch back to Microsoft Teams, okay? And I will share my slides with you over there, and we can have a discussion. Thank you so much for your attention, and I hope this was a fun experience for you.
Okay.
All right, I'm back.
Okay. All right. So let's give everybody 30 more seconds just to get back. So I think I will speak for myself, but I think I speak for a lot of us. We need to re-invite Tony really soon so that he can teach us how to do that.
Thank you.
But that was pretty awesome.
Thank you.
I must say, yeah, that's yeah. Okay. Well, I think I know what I'm doing in the next few days, learning how to use YouTube.
Thank you very much, Hugh. Thank you.
So learning to use YouTube, not only to look to find footage of the World Championship of skiing and biathlon. Well, so that was extremely interesting, and I'll first, I think we are at the end of the talk, and we have a few minutes for questions. I mean, we can stay as long as we want. I do have a hard cutoff at 2:40, but does anyone have any question? You can unmute yourself and ask. I have plenty of questions.
Hi, thank you for that talk. That was really interesting. Did you get any comments from the orchestra? I don't remember if you said about changes in audio. It sounded like it sounded good, right? But I was wondering if maybe the the people playing instruments might have had a more of a nuanced feel for anything that felt different to them.
Yeah, so it was a concern for the orchestra, and to be honest, we do not know if they ended up adopting all the strategies we proposed. They might have had some rearrangement here and there, but the message we got after we spoke to the conductor. He said, "I will do anything possible to keep my orchestra safe." And moving on, I think so. Our analysis was only one piece of the puzzle for them. They were consulting with others as well in public health, and there were other constraints coming from the state and from the county. So all of those played together. They leveraged our results as evidence to say whether they play or not. What I know is that they were the second, only one of two symphonies open in the United States for live performances. And I think they would do a circuit breaker every now and then. They would switch back to online performances via Zoom or something. But within themselves, they had more confidence to play closer to each other if the doors were open. And so they were probably rehearsing that way, even for the online performances. We did not keep track of all of that, because once the contract ended, we had classes to teach and follow up, etc.
Yeah, that's phenomenal. That's a really really cool example. Really cool problem you solved.
Definitely.
Jeff, you got a question?
Hey, Tony.
Hi, Jeff.
Yeah, congratulations on pulling off a 3-month study like that. I know how hard that can be. That's crazy hard. I also was really impressed with the Zoom thing, or the YouTube thing. That was neat. I wanted to ask though, I know you only had a short time to do the study, but I wanted to ask about the effect of boundary conditions on the front and the back. It kind of seemed to me like those big recirculation vortices might have been affected, especially in the front, by the front boundary condition.
That's right.
Have you looked at that?
We did look at that. So we did not put a wall over there. We just put an open boundary. There was some flow going through it. It was like a transparent boundary condition. There was some flow going through it. But when we went and did measurements, the velocities at the curtain were about 2 orders of magnitude lower than what's on the stage. Now, there was one simulation we did where now in their live performances, they actually extended the stage by about one length of the stage. So they moved the audience even further back away from the stage. Now, we did do that calculation with doubling the stage size, and we measured the flow across that. And it was within acceptable error, that's second order within our overall calculation. So we were not too worried about that. But there is an impact. Definitely there is an impact. As we were exploring this, you're probably a CFD practitioner, and boundary conditions can be a nightmare. They could change your flow field entirely. And we had some trouble early on figuring out the best boundary condition there. But the guideline was what we expected the measurements to give us on average. Again, there was no verification analysis or validation after all. Well, the verification of the code is verified and well verified each individual model, and when you put them together. But we didn't do extreme validation. We didn't have the time. It's an engineering analysis, right? It's an engineering study, and again, I have a person, I have a newborn, and we have people at risk at home, and I was willing to go down there and stand over there, and completely comfortable. Yeah.
Great. Thanks.
Thank you. Will.
Bill, why don't you go ahead?
Thank you. Really appreciated this talk, especially as someone with a growing personal interest in fluid dynamics. That was fascinating.
That's great.
And I was curious if you'd had any individuals or organizations approach you about designing new spaces using some of your techniques or findings, and what you think that might look like.
Yeah, so we were not specific. We were approached by a few other orchestral type people, because when the orchestra announced to the other orchestra conference, the other orchestras in the US, many orchestras asked us for a copy of our report, for example, for some of the results of simulations, and those were publicly available, and we were happy to give those to them. We consulted with one orchestra. We typed a report for them on what they could do for their performance. But we were not specifically approached to design a new venue. Well, there was one case, but the price would have been high, and that's why we need these low order calculations. If we had these potential flow or mass conserving type calculations that are corrected for momentum balance and reasonably correct, so you satisfy mass very well, and then you adjust for whatever momentum wants to do, so we can spin up these calculations really fast, then that would make it a very low cost service to provide to everyone. I mean, heck, you could put it online, and that was part of the proposal, actually, is to design a web-based utility to provide the community with all of these results. And you can do essentially active learning if you're doing an AI with it. You can keep teaching the model to improve by feeding it new simulations that we're running offline.
That would be an amazing tool for so many reasons.
Yeah, but now the pandemic, is winding down, and when the vaccines arrive, this probably is not going to be a major concern. But again, who wants to get the flu, right? Or who wants to get a cold? Even if something as benign as a cold can keep you miserable for 2 weeks, right? So, maybe just by reorganizing I personally, when I go to the grocery store now or to a mall, I try to stand as close to the doors or in the line of the air conditioning as possible. Thanks, Will.
Thank you.
Isabella, why don't you go ahead?
Hi, just first of all, once again, reiterating what everyone said, that was a fantastic talk. So
thank you so
I'm glad
much,
I was
Isabella.
here to see it.
Thank you.
I know you were very crunched for time to do this, so this may be kind of a general question, but if there is anything you could add to your simulation or perhaps change looking back at it, is there anything that stands out to you that you wish you could have done?
Yes, I would add a scalar model for settling and evaporation, because that might change the overall concentration. We could say once it's settled, it disappears, right? And once it's evaporated, although it might be that the DNA of the virus itself or the RNA or whatever is in the virus might still be floating around, right? But we could assume that disappears, so that might lead to potentially lower concentration. And one more thing, I want to play at peace in a simulation. So as I control the emissions, I could put a time-dependent, to be technical, I could put a time-dependent source near the flute and the trumpet and make it play an actual music piece. So it would emit, for 10 seconds, and then the other instrument would emit, and see more of a, realistically what would happen. But it was rewarding to say that this is the worst case scenario. The real life scenario might be better, but the worst case scenario, if we can figure that out, we're probably going to be okay in real life. But those are the things I would do if I had more time.
Yeah, that makes sense. Thank you.
Thank you.
Any other questions? Can you raise your hand? So while I give people a few minutes to think about the question, if they have any, well, I do have some questions, Tony. So one of them is, what were the velocities above the head of the players, like the typical flow velocity above the head of the music player, like?
About somewhere between 0.1 to somewhere between 0.4 to 0.5 meter per second. So if you look at the,
so it's quite quite significant, right? Because HVAC norms tend to be, like the comfort level is around 15 centimeter per second, right? 0.15.
It still felt comfortable though. I mean, it was breezy, but it still felt comfortable.
But it was breezy.
It was breezy.
Okay.
Yeah.
No, I mean, so.
And it might have to do with their need to maintain a certain level of humidity for the instruments.
Mm-hmm. Yeah. No, awesome study. So which code did you use to do that?
So we have our own code called Wasatch. I started developing that when I was a postdoc here at the U in 2010. It's a finite volume, fully structured code that is part of Uinta that you mentioned. Uinta is sort of the MATLAB where you develop your applications in. So Uinta gives us a strategy to do asynchronous parallel communication, domain decomposition, defining complex geometries, etc. And then we put in an application code that solves a particular set of partial differential equations. So that would be Wasatch, our code. It's finite volume, fully structured code, because Uinta is fully structured. Now, the reason we go with structured is because we want to go to extreme performance. So, our code scales 500,000 cores, no problem. 18,000 GPUs on Titan, no problem, because we are structured. Now, that means we cannot represent. So we do not have AMR with our projection method because we are fully staggered. And we do not have, so the pitfall is complex geometry. You're not going to have the nice smooth surfaces. You're going to have some rugged surfaces. But I like that because it tends to create some additional turbulence, right? As the flow moves around and starts, breaking down. It's fully explicit too.
I was going to say, well, the explicit does help with scaling. Implicit is, but unfortunately, sometimes you have to implicit something.
Yeah.
So in your structured code, the cylinder that we saw, was that immersed boundary method or
no.
Do you measure?
It's very simple. So that was done. Essentially, we use a on-off, not immersed boundary. We just have a scalar field called volume fraction, and if the fluid volume fraction is 1, that's fluid. If it's 0, and then with a scalar field, all you do to zero out your fluxes, you just interpolate that volume field to the surfaces, for example, and then you multiply with the flux, and bam, you got. So that adds up to the speed of the calculation, but it's not an immersed boundary method.
Okay. Yeah.
Well, it's not. Yeah, it's not.
One could argue. We had a similar method at Stanford. We call that blanking. But so that's the. No, I think what's really interesting in your work, and you and I have seen many papers based on RANs. And quite frankly, physics of fluids has managed in one summer to convince me never to publish in physics of fluids ever again.
Why not?
Well, just look at all the papers coming out of there on COVID and RANs, right? And the issue is that you look at the recommendation that are made based on those papers, and you see those aerosol and whatever dropping down like lead, and it's not okay.
It's not. That's right.
So but I really like obviously the whole simulation that you did, and the ventilation piece is extremely challenging. I tried to do a really high fidelity simulation of an air purifier in a small room, and we have similar code. My code is unstructured, but still scales really well. And it was going to take me 100 days.
How many cores were you using?
So I had 100 million cell, and I was using. I could use up to 10,000. I could it didn't matter.
Okay.
Thanks, Nick.
Bye.
It's running late. I gotta go. Thank you so much, Tony. That was awesome. I'm glad the YouTube streaming seemed to work for everyone. Just gonna ask real quick. I don't mean to interrupt, but I do have another meeting at 2:30. Does that link that you send out when you finish the presentation, can people just go to that same link?
I believe so. They can still play on it, but if not, I will, once I end the stream, I will trim out the initial parts, and then I'll send you the final link when I publish it. Okay, and then you can share it with everyone. Yes.
Yeah, we've had students ask about it, so yeah, just whenever that happens, if you could let me know. But thank you again. This was fun.
Thank you very much, Nicolo. Bye-bye.
Yeah, bye-bye.
Yeah, so more access to more cores, would that have helped you?
No, because at the end of the day, the issue is the time scale. You need it, like, in order to answer the question, does an air purifier, a simple air purifier that you can purchase on Amazon, help? You need to simulate that for 20 minutes. The 10 first minutes, right? Like an ACH of 6, so 10 minutes. The first 10 minutes is just garbage, right? You need to let
flush
the flow
the initial
settle
condition.
Exactly. And so it was not like the time step, because we have particles, right? So we have Lagrangian transports and everything else. The time step was like 5 × 10⁻⁵, right? And now you're looking at a huge number of iterations. So now the issue.
Are you implicit on diffusion, or just fully explicit everywhere?
No, we can, like you, we can switch. Okay. We can switch, but really the issue is that what we do, the LAS, what I've come to conclusion is that, like you know, like I like what you say, we need to work on rants. Now, I have done work on rants and rants model. I can tell you that I don't see any solution soon. The rants models are intrinsically lacking some key element of the physics that we may not fully understand, especially when it comes to scalar transport. But at the same time, running hundreds of LES simulation is just not practical.
Absolutely. But it also depends on what you're interested in, right? So, in a large hallway like that, maybe the RANS is going to capture the bulk flow, but it's not going to capture the local dynamics very well, right? And if maybe that doesn't matter then. If you're capturing the bulk flow, taking a worst case scenario, that's how we justified some of the assumptions we made. In the end, this is a back of the envelope calculation on a very expensive envelope, right? Which is the LES, but there are some corners we have to cut just to make this feasible, right?
So I would tell you this, is that like this is where we are right now, and we are interested in flows that are below 10 centimeters per second, because the bottom line is that in most super spreader event, there is not strong ventilation. People are not coughing or speaking loudly constantly. Okay, sure, there was the choir, but that was one of them. And so what you realize, and that's, like I'm generating, terabytes upon terabyte of data, but you realize that those centimeter per second flow that you cannot feel, by the way, your skin cannot feel those, they go anywhere.
Yep.
But then, of course, the time scale is huge. So and of course, rants, if you try to do a rants with that, it's going to say there is no flow. Like there is no turbulence, there is nothing going on, right? So rants right there just breaks down entirely. And the issue is that for us, even with great scaling, with great numerical method, we are still, cannot wait for quantum. Any other question from the audience? Because unfortunately, I'm going to have to go my PT appointment.
Yeah, and I'll respond to your email. I'm just coordinating a few things, and I'll let you know.
Well, it does, look, Tony, it doesn't have to be this week. We can also talk next week if
Probably
it's
better
easier for you.
Probably better next week. Yeah.
Let's do that. So Andrew, Fukian, George, Isabella, no, do you have any question? Will, like?
I assume that's your team.
No, well, Isabella and George. So George is working on genetic algorithm plugged into the computer to our software for optimization.
Okay.
Isabella is working on COVID project. And Fukian is working on elastoinertial turbulence, the turbulence generated by polymers. It's not COVID.
Okay.
Although there is a future where I'm going to plug my viscoelastic model to look at. We lost Tony?
No, I'm here. I'm here. Sorry, I pressed the wrong button on the camera.
Yeah, so we're going to look in the future at atomization. And of course, saliva is non-Newtonian. So,
yeah, and that's So if you're capturing with the slow speed flow, what is behind the spread and time scales? Are you also capturing a significantly different scale of a sneeze, for example, in that low flow? Because if your flow is
we don't do sneeze, we do just breathing. So like when you breathe,
and that's where
so basically this is the pattern of breathing,
and that's the spread in scale. That's going to give you the spread in the scales.
Like the aerosol rise up not by buoyancy, because by that time they are in full equilibrium with air, but the vortices basically tilt up, and then through induced velocity they keep rising up. The issue is that the velocity of rise is centimeter per second, literally, right? So knowing that the breathing does this, you can put your hand here, you don't feel anything, right? But it's still there. And of course, like if you have like a 5 centimeter like wind going this way, well,
it's gonna goes to anywhere. Yep.
But so that's the fun part. But let's talk next week, and
of course I'll respond to your email and we'll set something up.
Okay. Actually, Isabella is the one who's going to finish writing the article for your issue.
Oh, that'd be great.
Yes, to put her on the spot.
I can't wait for your article. If you want to put in even more, feel free. We're open. We're accepting all submissions.
Okay, that works. Hi.
Great.
Talk to you soon.
Thank you so much.
Bye.
It was a pleasure. Bye.
Thank you so much for your time. Bye.
Thank you. Bye.
Thank you.